So, hello guys, welcome back. And today we'll be discussing about the stories of real numbers. And the motto of these sessions is to just share the knowledge out there, which are not important for the exams. But if you love the subject, then you are, um, invited to join the discussion session. Regarding the discussion, it will be today's discussion will be around how the ideas of real number evolved. Okay, because straight away when we start preparing for exams, we go into sequence and series right away, but we don't know how real numbers, the numbers that are so beautiful, have actually developed in the uh, the time in the chronological order in the history of numbers. So the goal of today's sharing and offering is to share the story of numbers. It's a part one. There's a part two also, and I will be sharing about what we are planning to do in the part two at the end of the video. So stay tuned. Let's understand this very carefully. That um, this goal of like understanding real numbers starts with natural numbers. Just give me a moment so that I can share the slide with you. Perfect. So now observe that let's go through the history. Okay, so first, like I have drawn some pictures on the board so to make you understand that. So let's say when we started learning numbers, so how natural numbers actually came into existence. So if you remember, natural numbers came into existence. If you like, you must not be remembering that, but in the history of mathematics, it's told like people are trying to understand the relationship between five fingers and leaves. Okay, five leaves. Okay, so they're trying to understand how to count both of them. So the natural numbers came up in that order, that how to connect five fingers and five leaves together. And the relationship of that is actually what is the development and the building up and the discovery of natural invention of natural numbers. So the perfect mathematical definition of natural numbers evolved from the fact that they want to count. Okay, it's called Peano's axioms. So 1, 2, 3, 4, 5. This way the natural numbers were defined and they developed, and it's like one counting 1, 2, 3, 4, 5, just like this, if you can see me. So now then what happened? Then that led to the discovery of natural numbers and zero. Okay, and then with zero, and then it led to the discovery and invention of integers, and then it led to rational numbers, and then it led to the final real numbers. Okay, irrational numbers and real numbers. So the development, the idea of sequences and limits, this came, if you see that if we each of them developed as a result of questions. Okay, certain questions mathematicians have asked, and those are very fundamental questions in mathematics, and if you try to understand numbers, and that led to the development of this whole range of thoughts and ideas. So let's first go back to the two operations that are really very close to the heart of numbers. So addition and multiplication. Okay, these two operations are very close in the heart of numbers, because if two numbers are added or multiplied, still it's a number. Okay, and there are also subtraction and division also, but it's actually very closely related to this. So that is the core idea of the next step. So the numbers, so there are two main operations, like mathematical operations. You have numbers, and they're added or multiplied to give new numbers. Okay, so if you observe the first question to go how the discovery of zero. Okay, if you are interested in the discovery of zero, that was the first question. So how did that actually happen? Okay, so initially there were 1, 2, 3, 4, and it's defined as natural numbers, as you know. And people ask the question that what if, like, what is that number if you add to 1, because numbers can be added, right? So what is that number if you add to 1, it will still remain the same? They ask this very fundamental question, and the result of that is actually what we know as zero. Okay, that's called the idea. That's the idea of the zero. That's called the zero element. Okay, and that's the definition of zero. It's a number which, when added to every number, it gives the same number back under the operation plus. And then when we have 0, we started asking more questions. What is the more question? The more question is revolving around the fact that what if you add, what number should I add to 1729 to get back to 1? What is that number? Because we know that number addition. Okay, so this is the idea where it's called like what number if we add to 1 it will give 0. Also you can write it as what number if we add to 1 that will give rise to 0, because we already invented 0, right? So that was the starting point of the development and the discovery of integers. So what number should we add to 0? 1 to make it 0. So that's the idea of -1, and that's called lovingly in the the linguistic of mathematics or language of numbers, it's called the inverse. Okay, the inverse of the inverse operation of addition, and that's where the subtraction came up. So the subtraction and addition are closely related in this aspect. Okay, subtraction is the inverse operation of addition, and that led to the fact and discovery of integers from 0 1 2 3 4, this whole numbers. Okay, this natural numbers union 0, that led to the development of this integers. So we asked two questions. Number one, it is the development of 0, that was x plus 1 is equal to 1, and the next question is 0, because we already discovered 0. So these two questions together actually led to the development of integers, negative numbers. So what are the next steps for the other discovery of numbers? The next steps are really, really simple, and they're very intriguing and enticing, to the human mind. So there's the next question that, so as I told, till now we have dealt with only two operations. Okay, we have only dealt with one operation out of the two operations I have mentioned to you. The first one is addition, but we have still the multiplication also. So the mathematicians and the philosophers of the time, they asked that, okay, we have found out all the things about addition and the inverse of addition and the 0. Now what about multiplication? We know, number one, we know that if you multiply any number with 1, it gives to 1. It gives to the same number. So under the operation of multiplication, 1 is it's called the 0. Okay, I mean, under the if you multiply 1 with any number, it gives us the same number. That's the idea of 0. That's the idea of unity in some sense. So the people asked, from while moving from integers to rational numbers, people asked this question: what number, okay, what number you should multiply with any integer a to get another integer b? What number you should multiply? That was a fundamental question people asked. What number you should multiply with any integer a to get another integer b? And that led to the discovery of rational numbers. These are the rational numbers. Okay, you see, these are the integers. This is the rational number on the right hand side. It was the whole number over here. That is natural number union 0. I hope my definition of whole numbers are correct. I define whole number as 0 union natural numbers. And here is z. And here we moved from natural numbers to whole numbers via this operation. And via this question, we move from whole numbers to integers via this question. Now, the inverse of addition. Now we are moving from integers to rational number by asking the simple question that, does there exist any number which when multiplied by 2 gives b or gives 3? Okay, it's like asking what is the natural number. And we know fractions because that's very evident in when you're cutting a cake. So that was very evident to the the people at that time, that you can divide into some aspects. Okay, so they know the idea of division at that time. Okay, because they're dividing the plots of farm fields, and they're dividing the plots, the cakes or whatever they're eating, so they're dividing into pieces. So they have this intuitive sense of division. Okay, and that is how, by this asking this fundamental question, what number if you multiply with another number a gives another number b? If you ask this question, this gives rise to the idea of rational numbers. Okay, and if because this is how it's defined as b by a. So we have seen these three questions leading from, first there is natural numbers that I have defined, I have told, and then it moves ahead to the whole numbers, natural numbers union 0 by asking the first question, and then it moves to integers by asking the second question, and from integers they move to rational numbers by asking this third question: what number multiplied by this a gives rise to b? So this is how the rational numbers, all the numbers, integers, whole numbers, rational numbers, all this developed till this point of time. Now, at that time, also there's an interesting thing happened. Pythagoras theorem was discovered, much before that around. And so, I mean, they knew about Pythagoras theorem. Let's not talk about the time of discovery, but they knew about the idea of Pythagoras theorem. One second, guys, I'm sorry. They knew about the ideas of Pythagoras theorem. So, what really happened? So they asked this next question. Oh, sorry, someone is calling and this is not disturbing me. I'm sorry for this. Yes, so now the next question is, so that came from the idea of Pythagoras, that, okay, so we know the number 1, okay? So what if we can form a square out of 1? You see, geometry was discovered much before around that point, so they know how to compute with geometry, and they knew square roots, okay? And Pythagoras theorem was discovered, they knew squares. So Pythagoras theorem was, so they asked that, okay, let's take a square of length 1, and then what is the length of this diagonal? We know that's root 2, right? We know that's root 2. So the question was, we have learned integers, we have learned, natural numbers, integers, rational numbers, but that point of time the philosopher was very confused, okay? That where do this, where do this root 2, what is this number? Because we cannot understand root 2, what is this root 2? Like, because they only knew just rational numbers, they didn't know root 2, right? They were totally perplexed around, at that time, that where is this root 2 coming from? Like, how we can show, like, what type of number it is? I mean, it's like discovering a UFO in the sky. Wow. So they were totally absorbed in understanding root 2. And we know that we have a very famous proof, in your school days, that root 2 is actually not a rational number. How we can show that? We can show that root 2 is equal to p by q. We can assume that it's a rational number, and then we square it. Okay, 2 is equal to p squared by q square. And from here you can, that 2q square is equal to p square. You can use this idea. And then these are all integers, okay? Remember, there is integers. And you understand that 2q square is equal to p square, so that p must be an even number, right? So let's assume that p and q are co-prime, okay? Because that's the definition of a good fraction, okay? The reduced fraction. They are co-prime. That means they have no common divisors. So 2q square is equal to p square, and then we understand that 2 must divide p, because p must be an even number, right? So because 2 must divide p, because that's an even, p is an even number, so we get p is equal to 2 alpha. So we replace that, so we get q square is equal to, q square is equal to 2 square alpha square, that is 4 alpha square. And from here we get q square is equal to 2 alpha square. So now observe from here very critically, okay? Observe from here very critically that this also gives that 2 divides q. That means q is also an even number. Let's say q is equal to 2 beta. So observe that the GCD of p and q is now more than 2, at least is equal to 2. That means what? It's corroborating the fact that p and q are co-prime, which phase. So people were now perplexed. They did this proof somehow, and they were perplexed that, wow, what kind of number it is? It's not a rational number. Then what kind of number it is? How it's fitting into the whole model of numbers? They were very astonished, okay, and they were really thrilled about the discovery of something, like we are. If we discover a new island, we are really thrilled about it. So this is the question 3.1, because we have not got to question 4, okay, which was the development of rational numbers to real numbers. So they discovered this question 3.1, like, what is root 2, okay? And they saw that, they found that it's not a rational number. Then what type of number it is? This length of the square. So that is when they defined irrational numbers, okay? That is when they defined irrational numbers. The irrational numbers were defined in this way, that Thank you, Shivanjan, for the nice words. The rational numbers were defined in this way, that it is something not rational, and that's the discovery of rational numbers. Around the time, lot of interesting ideas and questions were coming into the minds of human beings. Okay, so they were asking the following questions: that what are those rational numbers? How we can define those? Because we have a very specific form of rational numbers. Okay, p by q, where p and q are integers. But what are those irrational numbers? How do they look like? How can I represent p and root 2? Okay, and can we get this just like we got rational numbers from integers, right? By that question, are there any questions that we can get we can answer, and we can get these rational numbers from these rational numbers? We've also seen that root 2 is an irrational number, right? So we asked that, can we just get these numbers by rooting, square rooting or cube rooting and stuff like that? And that's when these ideas came up, that this ideas came up that of rational numbers, and you will get to know how it's happening. So if you see this, if you read this publication book, it's a really beautiful book, you should read it. Now if you read this book, you will see that, I mean, how this idea that, if you observe, there is something called constructible numbers. You remember, you have done in your high school compass, geometry, and all stuff, right? So there's something called constructible numbers. You can construct certain numbers, you cannot. So you can prove that, those who which are square roots and stuff like that, that can be constructed. Okay, there's proof like that. We like really beautiful. You can find it out. Okay, but the question is that what type of number is pi? Is pi rational or irrational? And there is a proof of that. So people want to understand that which numbers are rational, which numbers are irrational. They were totally absorbed in it, and they have been mathematical war. Okay. Now when you go into this depth, that how to get these irrational numbers from rational numbers, this question only. Discovered the calculus. Okay, it's a different way of calculus discovered by Newton. Newton discovered the calculus in this way. Newton discovered the calculus in the way of, finding the tangent and the velocity. They discovered differently entire, okay, how to create new numbers, what are the philosophical existence of numbers. Okay, and that was the birth of these real numbers. Okay, and that is where the storyline of discovery of rational numbers, that how we can approximate, how we can go towards the towards the irrational number by a sequence of rational numbers. Every such number in the real number line, every so the idea is that how was this numbers moved to irrational numbers or real numbers? That is the idea of limit, and that is the question 4. That if we take a sequence of rational numbers, so let me give you an example. So you have a root 2, right? So root 2 has an expansion. So if you just search root 2 expansion, if you just search root 2 in Google, you will just get an expansion, right? So let me just write the expansion of root 2 in decimal expansion, I mean. So if you write the expansion of root 2, it's like 1.4142, right? 1.4142. So let me write it down. So 1.142 dot dot dot. So observe that each of this, so you can find a sequence like this. First sequence element is 1. Next sequence element is 1.4. It is 1.41. Like sequence third element, I mean. This is the fourth element, and this is the fifth element. Okay, and this goes on, an infinite sequence of numbers. And this is how people have tried to understand that how limit of rational numbers. So the idea was discovered. This is how the sequence and the limit, these concepts are discovered, guys. So I hope you enjoy the session, guys. In the part 2 of this, we'll continue the idea of which questions are really important for understanding this limit and sequence. the idea, the limit and sequence is the stepping stone for understanding how rational numbers can be used to define any number. Okay, by rational numbers and limit, you can understand any number, and that's the beauty of this. That's how we discovered limit and sequence, not as a very discrete topic that we learn in our for any examinations out there. Okay, we understand this just because we love the depth and the discovery. It helps us in discovering numbers. Okay, so I hope you enjoyed the session, guys. If you do enjoy it, do share it among your friends and people do like it. And yeah, that's how you encourage us, guys. So thank you so much. In the part 2, we will be discovering about how we can use this rational numbers to discover these real numbers. So just having a small wrapping up of the whole thing. So today we discovered this question one, how natural numbers can be extended to zero, add zero to it, and then using this we can how we can ask questions to get integers, and then using that how we can get to rational numbers. And finally we got that how question 4 is actually nothing but the idea of limit and sequence, and that we'll be learning in our next part 2, guys. This is not related to exams, so enjoy it, guys, and all the best. I will see you in the next video. Thanks for your support. Stay tuned and stay blessed. Bye bye.